Welcome to today's presentation. This slide doesn't contain enough information. That's why we're moving to the next slide. High-frequency signals, like those in the UHF and VHF ranges, require a clear, unobstructed path because of their short wavelengths, which naturally limit how far they can travel. This means that for effective communication, these signals need a direct line of sight. However, when we want to extend their reach beyond the horizon, we turn to a fascinating atmospheric phenomenon called tropospheric ducting. Ducting involves the guiding of radio waves through the atmosphere via successive refraction, which is essentially bending of the waves. This process is known as superrefraction, and it allows high-frequency signals to travel much farther than they normally would, sometimes up to 1,000 kilometers. What makes this possible is that these ducts act like invisible tunnels, channeling the signals through the lower atmosphere without needing a direct line of sight. This is particularly useful for long-distance communication, as it enables signals to reach targets far beyond the horizon, effectively extending the range of our high-frequency transmissions. So, in summary, duct propagation through superrefraction is a key technique that allows us to utilize high-frequency signals over much larger distances, overcoming the natural limitations imposed by wavelength and line-of-sight requirements. This phenomenon plays a crucial role in atmospheric radio wave propagation and has significant implications for communication systems. Let's talk about the duct. Essentially, it's the region of cool air that exists between layers of warmer air. Think of it as a cool corridor trapped within a warmer environment. This formation of the duct is actually the result of temperature inversion, where a layer of warm air sits above cooler air, creating a kind of barrier. This phenomenon is crucial because it leads to what we call superrefraction in the atmosphere. Superrefraction significantly affects how radio waves travel, often bending signals further than they normally would. Understanding this helps us grasp the bigger picture of atmospheric behavior and its impact on communication and navigation systems. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Multi-hop propagation is a fascinating mode of radio wave transmission, especially used for high-frequency, or HF, signals. What happens here is that the radio waves don't just travel in a straight line. Instead, they bounce multiple times between the Earth's surface and the ionosphere. This bouncing or reflection process is what we call multi-hop propagation. The key point to remember is that this process effectively extends the communication range far beyond what we would expect from line-of-sight transmission alone. So, instead of being limited to just the distance visible in a straight line, signals can reach much farther, even across continents or around the globe. This capability is crucial for global communication, especially in areas where other forms of transmission might not be feasible or reliable. It highlights how understanding and utilizing natural phenomena like the ionosphere can significantly enhance our communication networks. In the context of our overall discussion on radio wave propagation, multi-hop propagation demonstrates how leveraging the Earth's ionosphere can overcome the limitations of direct line-of-sight methods, opening up new possibilities for long-distance communication. Let's talk about the need for multi-hop propagation. Sometimes, direct communication just isn't feasible. This could be due to various reasons like distance, obstacles blocking the signal, energy constraints, or even reliability issues. To overcome these challenges, we use multi-hop propagation. This approach involves using intermediate relays, or hops, to extend the coverage area. By doing so, we can achieve longer reach, reduce power consumption, and improve overall reliability. Now, how does this process work? A radio signal doesn't just travel in a straight line. It propagates through a series of hops. Each hop involves reflections, where the signal bounces off objects or surfaces. Think of it as the signal taking several smaller steps rather than one long leap, making communication more effective over complex environments. This method really helps us build more robust and energy-efficient wireless networks. Now, let's talk about how an HF signal makes its journey through the atmosphere. It all starts with a transmitter on Earth sending a radio wave skyward at a specific angle. This is the initial step in our radio waves voyage. Once the signal travels upward, it reaches the ionosphere, which is a layer of the Earth's upper atmosphere that's become ionized by solar radiation. Here, where it gets interesting, because the ionosphere's plasma-like properties cause the radio wave to bend, what we call refraction, it doesn't just pass through into space. Instead, it's reflected back down toward Earth. From there, the signal hits the Earth's surface, whether that's land, water, or a combination of both, and bounces off it. This reflection sends the wave right back up toward the ionosphere, creating what we call a second hop. And this bouncing process can repeat multiple times, back and forth, until the signal finally reaches the receiver antenna at a distant location. The number of hops depends on factors like the frequency used and atmospheric conditions, but in essence, this bouncing allows HF radio signals to cover vast distances that would otherwise be impossible with direct line-of-sight communication. So, in summary, this cycle of transmission, reflection, and bouncing is what enables long-distance radio communication using the ionosphere as a kind of natural mirror. Let's take a closer look at how it works. In a simple, direct communication setup, data travels straight from the source to the destination in what's called a single-hop process. It's like sending a message directly without any stops along the way. However, in more complex scenarios, especially when the distance is long or obstacles are present, we use multi-hop communication. Here, the message hops through intermediate nodes or relays before reaching the final destination. You can think of it as passing a baton from one person to the next until it reaches the finish line. Now, at each of these intermediate nodes, a crucial process happens. The received signal is either amplified and forwarded or decoded, and then retransmitted. This step is essential to ensure that the signal remains strong and clear as it travels further. The relay process continues, hop by hop, until the message finally arrives at the destination. This method helps extend the communication range and improves reliability, which ties back to our overall theme of building efficient, resilient wireless networks. Now, let's talk about some key factors that influence multi-hop propagation. First, frequency plays a crucial role. The frequency of the radio wave is critical because it determines whether the wave will be refracted by the ionosphere or not. If the frequency is too high, the wave won't be refracted at all and will just pass straight through into space, making it unusable for long-distance communication. On the other hand, if the frequency is too low, it may get absorbed by the D layer of the ionosphere during daylight hours. This absorption prevents the signal from reaching the higher, more reflective layers, which are essential for bouncing the signal back to Earth. Next, let's consider the ionospheric conditions themselves. The properties of the ionosphere, such as its electron density and height, don't stay constant. They change depending on the time of day, the season, and even solar activity. These variations can significantly affect the path, stability, and overall reliability of our signals. Finally, we have reflection losses. Each time our signal reflects off the Earth's surface or passes through a layer of the ionosphere, it loses some of its energy. These losses can weaken the signal over multiple hops, so understanding and managing these factors is key to effective long-distance communication. All these elements are interconnected and highlight why understanding the ionosphere and frequency management is so important in optimizing multi-hop propagation. Let's take a look at some of the advantages of this type of network. First, extended coverage means we can reach farther distances without needing additional infrastructure, which is a huge benefit in many scenarios. Better reliability is another key point. Since these networks can dynamically adapt and reroute around obstacles or failures, they tend to be more dependable. Energy efficiency is also important. Because devices can communicate directly or with fewer retransmissions, they often conserve power. Additionally, this approach overcomes obstacles effectively, making it useful in urban, hilly, or indoor environments where traditional networks might struggle. Now, of course, there are some disadvantages to keep in mind. Increased latency can occur due to multiple hops, meaning it takes longer for data to travel across the network. The routing and synchronization become more complex because each node needs to coordinate with others, which adds to the system's overall complexity. Plus, if noise or distortion accumulate at each hop, it can lead to cumulative errors, potentially impacting data integrity. Moving on to applications, these networks are quite versatile. They are used in wireless ad hoc networks, such as MANETs and VANETs, where infrastructure is limited or absent. Sensor networks are another key area, especially in IoT and environmental monitoring, where deploying a flexible, decentralized network is essential. Satellite constellations also rely on inter-satellite links to maintain global coverage and communication. And finally, these networks are critical in emergency or disaster situations, where existing infrastructure might be damaged or unavailable, allowing communication to be quickly re-established in challenging conditions. Now let's take a closer look at the multi-hop propagation modes. Starting with the single-hop single layer, this is the simplest form of communication. Here, the data travels directly from the source to the destination, with no relays or additional layers involved. Essentially, it's a point-to-point connection, often a line-of-sight or LOS link. For example, when a base station communicates directly with a mobile user, that's a classic case of this mode. Moving on to the single-hop multi-layer mode, things get a bit more interesting. In this scenario, the source still transmits to the destination within a single hop, but it does so via multiple relays operating simultaneously within one layer. These relays work in parallel to assist the transmission. The key benefit here is diversity gain, because the destination can combine signals coming from various relays, which improves reliability and performance. An example of this is cooperative relaying, where multiple relays forward the message at the same time in one hop, enhancing the robustness of the communication. Both modes are fundamental to understanding how multi-hop networks can be optimized for different scenarios, whether it's direct, simple links, or more complex relay-assisted transmissions. Let's take a look at the concept of multi-hop multi-layer relaying. In this setup, we have multiple relay stages, meaning signals are forwarded through several hops to reach their destination. Each of these stages can include multiple relays operating in parallel within a single layer. At each layer, more than one relay works together to forward the signal to the next layer, which helps improve the robustness of the communication. This approach provides two key benefits. First, it offers diversity, since multiple relays in a layer can transmit the same signal, reducing the chance of signal fatting. Second, it extends coverage because the signal can hop across longer distances through multiple layers, reaching areas that might be out of direct range. You can see practical examples of this in wireless mesh networks and ad hoc networks, where multiple relays cooperate to maintain reliable communication over larger areas. Additionally, cooperative diversity relaying in multi-hop scenarios leverages this layered, multi-relay structure to enhance overall network performance. Overall, this multi-hop, multi-layer approach plays a crucial role in expanding coverage and improving reliability in complex wireless environments, aligning perfectly with our goal of robust, scalable communication networks. This slide doesn't contain enough information. That's why we're moving to the next slide.